Okay, our goal is to prove that the diagonals of a parallelogram intersect at right angles if and only if it is a rhombus. Let's get a diagram drawn first. And I'm going to draw a parallelogram that looks a little bit like a rhombus, so I'm just hedging my bets a bit. So I need to put some labels on it. I'm going to use O in case we want an origin, A, B, C. Okay, we're going to let OA equal A as such. We're going to let OC equal C as such because we're going to use those. Now, if this quadrilateral is a rhombus, so if OABC is a rhombus, OA equals OC, or in other words, the magnitude of A equals the magnitude of C. Okay, that's if it is. We have to show that under the circumstances it becomes a rhombus. This is something we're going to look out for. Okay, you'll see this pop up towards the end of the proof. Okay, we're talking about diagonals. So we're going to generate some diagonals. I'm going to generate this diagonal. And I'm going to treat it as a vector. I'm going to generate this diagonal over here. As a vector. I'm going to put in some of that other information there that from earlier on, because it is a vector proof. Now, I reckon I'm going to need vector AB or something equivalent to that in terms of C, because we're looking at this diagonal here, for example. I'm not going to color it in, but the one that's going up that way, and that might involve AB. So I'm going to write down a relationship, vector AB is equal to vector OC. Geometrically, it is the same. Okay, so that geometric statement can be made. OB that's diagonal. Okay, so that's why I'm writing that, because it's a diagonal. Okay, so diagonal OB, you can see that here once again, diagonal OB, using vector addition, we can add two other vectors together, and diagonal OB is OA. Whoop, OA, it's being difficult, OA plus AB. Alright, so OA plus AB, but AB equals OC, so that's OA plus vector OC, which is A, lowercase a plus lowercase c. Okay, we need that statement. The other diagonal you can see is AC. So we need a statement for AC. The other diagonal, AC. Now AC going downwards is negative OA, because it's in the reverse direction going downwards. So negative OA plus OC goes across, which is negative A plus C, or C minus A. Either way, that's written in terms of lowercase a and c, which is the trick, okay? This is the goal of what we're trying to do. It's the strategy. Okay, right angles. So we're looking at those intersecting at right angles. So that usually means we're going to talk about the dot product of two vectors equaling 0. So OB and AC, if we dot them together, dot those vectors together, we have that dotted with that, lowercase c minus a. Alright, so just replacing in terms of these statements up here, and using the distributive rule for dot product. Okay, distributivity for dot product, we've got a dot c minus a dot a, first by first, first by second, second by first, second by second, plus c dot c minus c dot a. Now remember, scalar product, or the dot product, is commutative as well, so c dot a equals a dot c. So the first and the last terms cancel each other out. Okay, so you should remember that from the dot product, it's commutative. So c dot a dot c are the same. So if you subtract them, there's 0. The other thing you should remember too is something dotted with itself equals that. So a dot a is the magnitude of a squared. So we have magnitude of c squared minus the magnitude of a squared. Now that's what the dot product equals. Now basically, if they're at right angles, if OB is perpendicular at right angles to AC, then that relationship above OB dot AC equals 0, or that equals 0. And if that equals 0, which means that they're at right angles, that must mean those two things are equal to each other, the magnitude of C and the magnitude of A. So a very rapid recap. We write the statement down in English if it's not already given to us. What we're required to prove, we draw a suitable quadrilateral with all the features that we need, naming the points. We need a couple of vectors, that are linked to the initial point, which I've called O. You don't have to call it O. Some people start with A and they might have gone A, B, C, D, but that's one approach. We look at them in terms of lowercase vectors. We write down the important relationship for the shape we're looking at. So those two non-parallel sides are equal. That's a special feature of the rhombus. All right, so we're using our understanding of what makes a rhombus special, a special case, because that's what this proof is about. It's about a special case sort of. See, the if and only if shows us that, doesn't it? Okay, and then we make, this is jumping around nastily here, we make some further relationships using vector addition, and we try and reduce everything down to in terms of lowercase a and lowercase c. We look at the statement, it talks about the dot product because it talks about right angles, so the dot product would equal 0. So we look at the dot product in terms of the magnitude of each line, and that's what makes a rhombus special, because a rhombus doesn't just have equal opposite sides, but it also has all four sides the same length. And by choosing A and C, we're choosing sides that are non-parallel. And if they're If they're the same length, well then we've got a rhombus. So we're saying yes, they are intersecting at right angles, because that's basically given. We just got to show that all four sides are equal, and we do that right down the bottom there as the final thing. Okay, so they're intersecting at right angles, the dot product is 0, and according to our relationship here on this line, C must equal A, which means it's a rhombus.